Thank you so much, Nalini, for the kind introduction, and welcome everyone. As Nalini mentioned, I'm currently a professor at Vanderbilt University, but I actually wear many hats. And today I'll be talking about some work I'm doing in conjunction with my colleagues at Carnegie Mellon University's Software Engineering Institute. In particular, I'll be talking about architecting software systems for the future, a research agenda. So just give you a little bit of overview of this. I think it's pretty clear to anybody who works in research in our fields that we're increasingly dependent on software-reliant systems. And it goes without saying, many of these systems are systems where the right answer that is delivered too late becomes the wrong answer. So they're mission critical, they're safety critical. And these types of systems require an investment and a continued focus on continual innovation and improvement in terms of the theories, the practices, the tools, the platforms, and so on that we use to develop them. I think it's also probably pretty obvious to most people that because software is so ubiquitous, because software is eating the world, as Mark Andreessen liked to say, we have to figure out how to develop and assure software continuously. It's not just a one-shot endeavor. And we need to be able to get these capabilities inserted as rapidly as possible because the mission needs them, the consumers need them, we need them for many different purposes, as we'll talk about here shortly. As a consequence of this, there are new shifts in terms of future systems, the types of systems that we're developing that require innovation and R&D. In particular, I'm sure you're all familiar with the old adage, better, faster, cheaper, pick two. What we're needing today is to be able to get systems that are faster to market, reasonably affordable, because oftentimes they're not affordable, and good. And it's very hard to get all three of those qualities at the same time. We've gotten very good at being able to build systems fast. Whether we always build good systems fast, of course, is a bigger challenge. So because of all these dimensions and changes and trends, we're thinking at SEI, CMU's SEI, about how we can work together as a community in order to think about ways to redevelop and reevaluate software. And so this has led to a study that I'm going to be talking about today that will be released shortly. And this work is done in conjunction with members of DARPA, members of NSF, and many members of the research community that you probably all know. The basic idea here is to try to think together holistically how we can come together as an ecosystem, as a community, to create a multi-year research and development vision, strategy, and roadmap to help do a more effective job of engineering the next generation of software-reliant systems. This is what the cover looks like of the study report that will be coming out hopefully next month. We'd hope to release it this month, but you know how software-related schedules tend to slip a bit to the right, but I think we're going to be ready to go. We're doing our final rounds of reviews and approvals very shortly. So this will be available at the CMU SEI website very shortly. So let's talk about what the study is going to be presenting when it's released. So again, just kind of recap, software is obviously very, very essential to national and international competitiveness, innovation, security. If you take a look at reports that have come out over the past decade or so about the influence of software on the economy is very dependent on software-related features and capabilities. This goes for infrastructure, this goes for all the other application verticals like education, healthcare, entertainment, national security, and so on and so on. I don't have to motivate much of this because I think we're all very much aware of this. So if we want to be able to improve software quality and productivity to create good software, better, faster, cheaper, that's going to take a group effort. And the first thing we need to do is identify what some of the key challenges are to engineer these software-reliant systems. I'll talk more about this in a moment, but it's no big mystery that a lot of this involves using advances in data science, advances in machine learning, and other things to help do a better job of building software reliably, and also do a better job of building intelligent software that will be highly confident and certifiable and so on. What we've done here is develop a roadmap, which is for research, focusing on foundational software engineering principles and practices across key system types, some of which are here and have been for a while, others of which are emerging. Things like intelligent systems, obviously large-scale autonomous systems, safety-critical systems, and increasingly data-intensive systems. Now, you'll notice in my talk today, I'm not going to spend much time focusing on the cybersecurity aspects, which are obviously foundational and very important. I'm not going to spend a lot of time talking about networking research, and that's not because those topics aren't important to software and building software-intensive systems. It's really because there are other reports coming down the road from other folks who will be covering those topics in more detail. But so let's just take it as a statement of belief that having secure software is crucial to everything else I'm about to talk about. Another thing that's crucially important for those of us who are in the research enterprise as faculty or members of research groups at companies or government labs, it's really important to make sure that the powers that be understand the critical role that software plays. Oftentimes people take software for granted. Oftentimes people tend to focus on the hardware. This is a big problem in a lot of mission-oriented agencies where software is often an afterthought. It's also a big problem in terms of priorities for federal funding and other types of support you might get. And one of the reasons for that is that a lot of people think that industry is going to solve all the hard R&D problems. Now, there's certainly lots of great people doing important work in industry. However, that's not going to solve the generic problem for generic software. It's going to solve specific problems for specific groups that have specific customers and specific financial goals to reach. So really what we need is to think about how we can leverage the ecosystem holistically, that includes the federal government, in order to be able to advance in areas that otherwise probably won't get there for a long time, just relying on each company to do it individually. And of course, as foreshadowed by what I just said, this is really a group effort. This requires collaboration between people in government, program managers at places like DARPA, the NSF, mission-oriented agencies like NASA and NIH. Obviously, those of us in academia who like to do research and are really driving graduate students and postdocs and our colleagues to do better and better things. And of course, there's a huge important partnership with industry because they're the ones who are really out there day to day making things work or finding out when they don't work. So part of the study involved having an advisory board. I won't go through this in detail. The slides will be available. You can take a look and see who's a member of our august body of advisors. But we have folks like Deb Frinke, who used to be the science advisor at the NSA. She's now leading the national security sciences at Oak Ridge National Labs. Vince Cerf, who I'm sure you all know, who's one of the founders of the internet. People like Bill Shirless at CMU, and who's currently on loan to DARPA, and others. And I would also be remiss if I didn't point out my partners at the SEI, like Anita Carlton, John Goodenough, Ipek Oskaya, Mark Klein, and John Robert, who've done a great job helping to craft this report I'll be describing. So let's talk briefly about the new types of systems that require advances in R&D. Certain types of things we're doing a pretty good job of. Other types of things we still have a long way to go. So obviously one type of system or one where you need to be able to adapt to the mission as the mission changes. Think all the excitement that we see these days in terms of new space exploration systems. People like Richard Branson and Jeff Bezos and others trying to see who can get into space fastest, who can go to Mars quickest, cheapest, safest, and so on. Those are systems where once they're in flight, it's going to be quite difficult to bring them back to Earth and do some software patches. So these systems have to be able to adapt themselves on the fly. Another type of system that's increasingly important are systems that perform data fusion at very large scales. There's obviously lots and lots of systems that are like that these days. One that comes to mind, of course, would be weather prediction. We've had a lot of storms these days. You probably heard about hurricanes hitting the New England, New York area, which is very unusual. And being able to predict the path of these storms, which requires lots of data analysis, is very important for all kinds of economic and safety reasons and property value reasons. Highly available business enterprises. So the days don't go by when you don't hear about yet another failure of a system. Often these days they're ransomware attacks or other kinds of breaches. It's very clear that keeping systems going is crucially important for our economy. I'm sure you've seen over the past 6 months or so how attacks on oil pipelines, attacks on the production of food, and supply chain attacks are very disruptive to our economy. And in some cases, shutting down, like a quarter of the amount of food that's being produced for certain industries. So keeping these systems up and running is very important. And this is, of course, where safety and where security really dovetail in with software advances. Personal digital assistants that actually assist are important. I have some programs that will send me alerts when I've got meetings coming up, and they'll read my calendar and give me a heads up about what's coming on my daily schedule. But let's be honest, those aren't really very helpful. It would be much better if something could read my upcoming schedule and then give me a nice little portfolio of information about the people I'll be meeting. That would be a lot more useful. You've noticed, of course, undoubtedly over the past 18 months or so, we've been in a series of healthcare crises around the world due to the pandemic. But even before that point, there was lots of demand for more integrated, secure, and holistic approaches to personalized healthcare. And one of the problems we're wrestling with now with things like vaccines is it's pretty clear that one size doesn't fit all, and people have to make some choices about what they're going to use. It'd be much better if we could have a way to know ahead of time what types of vaccines would be appropriate, or different types of treatments or drugs, without having all kinds of harmful side effects. And then something else that's near and dear to my heart as someone who's done work in cyber-physical systems for decades, all the smart this and smart that. Smart cities, smart cars, smart roads, smart transportation systems, where we use computing devices that are aware of their surroundings in one way or another. So these are all examples of things that are coming out where we need more than just what's available off the shelf today. So what are some trends? Well, one trend, of course, is scale. So we are building bigger and bigger systems that are more interconnected. And we need to be able to compose those systems out of building block pieces because it's too hard to build them all from scratch. We'd also like to be able to get to the point where we can continually roll out new software and not have to worry about the time and effort and consequences of failing to reassure it. And this, of course, is particularly true for safety critical systems. There's also a big problem, as I'm sure you know, if you've tried to hire people lately, this includes grad students for that matter, we have a real skills gap in our workforce. A lot of people are very familiar with technologies that are not necessarily what we need today. So getting a way to retrain the workforce, crucially important. We, speaking as an educator, that's very important for us to do a good job of educating the next generation of people who will go out there and take on the world. Another problem, of course, is that from a curriculum point of view, we're increasingly teaching stuff that was important when we were grad students, but perhaps isn't the most important thing anymore. And trying to figure out how to structure the curriculum is very important as well. Obviously, everybody these days is very excited about artificial intelligence, which I like to think of less in terms of AI as a magic panacea with sprinkling pixie dust on things, and more about analysis of data and trying to find patterns in data, machine learning, deep learning, transfer learning, and so on. Another thing that's crucially important, I'll talk more about this, is making it possible to do evidence-based assurance from multiple sources of evidence, that be testing, formal methods, inspections, and so on, to make sure that these systems behave as intended, which is getting increasingly important as we have more AI-inspired solutions that are often less deterministic than what we're expecting in the past. Something else that sort of the other end of the spectrum that's important is increasingly we're integrating software with societal scale ecosystems, things like Facebook or TikTok or Twitter, and trying to make sure that the way that those systems work don't lead to very dysfunctional antisocial behavior is something that's now more important perhaps than ever before in human history. And then finally, another point, another trend that kind of underscores everything else I just mentioned. Data is becoming really the driver for a lot of this stuff. So we've often looked at algorithms, we've often looked at ways of scaling up computation through parallel processing and distributed computing, but increasingly it's the data and the quality of the data and the ability to make sense of what's in the data that's driving innovations in almost every sector in our economy. Okay, so that's just a kind of quick overview. Now let me get into more of the technical fun stuff here. So we worked with our advisory board, we did a lot of surveys of what's out there in the literature, talked to a lot of people. We held a bunch of workshops that were sponsored by NSF and DARPA. Sadly, they were all virtual, of course, for the last year or so, and then took a look at a lot of kind of future casting, what might be coming down the road. And the idea was to try to get a lot of input from a lot of key stakeholders in this space who have a role to play in what's happening. That's led to our report, which we're about to publish, which is the research roadmap, which was our attempt at trying to codify this in an actionable way, and I'll talk more about that in a moment. And then we hope when this gets released, we might have an impact. I've been involved in many studies over the years. Sometimes studies are really cool and they make a difference. Our ultra large scale systems study that we did at CMU, 2005 timeframe, had a nice impact in the research community for a number of years. But a lot of times studies just sit on the shelf and they don't really advance the practice at all. And that's not our goal. We're trying to get to the point where we can make a difference. And we hope to get help from everyone here to move forward on this. So let's talk a bit about what the vision is for the future of software and software engineering. Again, keep in mind that this is a software engineering centric focus. Doesn't mean that other things aren't important. It's just what we're focusing on here to keep the report tractable and in a manageable form. So the basic idea where we're building software largely manually with some support from tooling here and there will be replaced over time, I would say in the next decade or so, by one where the software pipeline, the tool chains and so on, consists of both people as well as AI, again, thinking about that in a broad sense, as trustworthy collaborators that can rapidly evolve systems based on user intent. So if you think about computing over the past 5 or 6 decades, it's been an inexorable move away from thinking like a computer to thinking more in a domain-centric way. Think, for example, of model-driven engineering as one little data point in that progression. And we need to go further to get it to the point where you don't have to spend as much time wrestling with the bits and bytes, and you can spend a lot more time thinking about what capabilities you want and let the computing systems help you in many parts along the way. Now, if we're going to do this, if we're going to achieve this vision, we need advances in kind of 2 different dimensions. One are new and improved development paradigms, and the other is in new and improved architectural paradigms. So let's talk about both of these things briefly, and then I'll go into some details. So the purpose, of course, of a development paradigm is to make it possible to build software more productively, more efficiently, and more assuredly, I guess is the best term. Make it so it's trustworthy at scale. Easy to build trustworthy systems that have 30 lines of code. Much harder to build trustworthy systems that have hundreds of millions of lines of code. So one thing, of course, that will be happening for sure is that humans will leverage trusted AI, and we'll talk more about that in a second, as a workforce multiplier for many of the aspects that we use to build and sustain software. So right now, of course, we've been doing automation for a long time, but a lot of that automation is very limited to sort of traditional things like your interactive development environment or your DevOps pipeline and so on. And we have a pretty good sense of how to do that. But as we get smarter and we get more data and we can do analysis of that data, we should be able to do a much better job of improving our software pipelines by leveraging this AI-inspired capability. Another thing that's important, maybe another way to look at this, is that in addition to doing things that are more experimental and more non-deterministic, we also have to find a way to do a better job of formally assuring that our systems are going to be correct. And we need to do this in a way where we can combine different forms of evidence, we can analyze them, again, in an integrated and a holistic way, in order to initially assure and then efficiently and cost-effectively reassure software as it evolves over its life cycle. And again, this is something that's extremely hard to do, especially for things like mission-critical and safety-critical systems today. And then something else that's very near and dear to my heart, because I've worked in this topic for decades, is to come up with advanced software composition techniques and mechanisms and smart composition tools and so on that will enable more predictable construction of systems at increasingly large scales out of pieces that are assembled together rather than being developed ad hoc from scratch. So those are some things we'll talk about here in more detail from a development point of view. Another thing, of course, that's happening is we need to have newer architectural ways of handling the development and the execution of the systems. And of course, the goal here is to be able to be more predictable and more secure and more scalable in our use of new and emerging computational models and paradigms. One good example is thinking about societal scale computing. We now have computer systems and social media platforms that are literally available anywhere on Earth and probably also to people in space stations, for example. And these systems are really very different in a lot of ways because they have a lot more emphasis on people and sociology and politics and economics and psychology. So it's not just about the technology anymore. It's about how these things are driving behaviors at scale and having quite an impact, as you no doubt see every time you turn on the news and find out ways in which people do crazy things because someone incented them to do that on social media platforms. So we talked before about using the AI to improve the way we build software. We also need to think of new ways to improve our software assurance techniques so that these AI-inspired systems actually behave responsibly and behave in a predictable way so they can be used in more safety-critical environments. And this is a very challenging dimension because a lot of the systems, a lot of the proof techniques, a lot of the testing tools that we've got to certify and validate our software don't have the assumptions about the intelligence that we're trying to put into them now in terms of the algorithms and the complexity and how long they take to run and how accurate the results are and so on. And then something else, of course, that's very exciting, potentially it's still sort of a pie in the sky dream, is how we'll be able to leverage new computational substrates, things like quantum computing, for example. And in particular, I'm not so much interested in the physics of the quantum computing as I am in how will we program these technologies in ways that will be productive and secure and allow us to be able to build the systems that we want at the scale that we want. So we came up with a software engineering roadmap to focus on these areas, and we took a look for the next decade or so in both the development and architectural paradigms. And the goal of this, of course, is to be able to allow humans to work together with trusted AI collaborators to rapidly evolve systems based on user intent, which is kind of a fuzzy term, but basically think about it as trying to describe the what as opposed to the how. And so that historically be programmed by systems that were driven by the how, the imperative stuff. And increasingly, we're trying to get to the point through things like functional programming and reactive programming and so on, where you're thinking more about the what you want, not the how to do it, and you let other parts of the pipeline do the translation from the what to the how. These are the 6 topic areas I'll be focusing on, and then there's a bunch of research goals and milestones and objectives, which I will talk about, but this is just a chart that puts it all into perspective, showing how we need to have a roadmap which will help hopefully incentivize funding agencies to put dollars behind this agenda so that we can all be better off, both in terms of doing the work and having an impact and transition. So let's briefly talk about these development paradigms in a bit more detail. I'll first, again, just briefly recap them, and then we'll go into about 4 of them in some depth to give you a better perspective of where we're headed. So the first one we'll talk about is AI augmented software development. And basically the idea here is to use machine learning techniques and transfer knowledge and other analysis approaches that are based on looking for patterns and trends in data in order to improve the way that we build software. So this is kind of, what they say, shoes to the shoemaker's children. We're trying to get smarter about how we use intelligent capabilities to build the software that will then go off and do other things for other purposes. Another key theme here, another development paradigm, is assuring continuously evolving systems. And we want to be able to do this so that we don't have to go back and reassure everything from scratch when there's small changes in the requirements, when there's small changes in the environments, when there's small changes in the implementations, and so on. Right now, that's very, very problematic, very, very long duration, very expensive, and not guaranteed to converge. Software construction through composition, rather than building systems out of pieces that are all built in an ad hoc way, manually, to historically trying to build them by assembling various components, some of which were designed to be composed, others of which were not designed to be composed. And this gets us into the whole topic of smart composition. How can you take components that exist in various parts of the ether, the ecosystem, the GitHub repositories around the world, and of varying provenance, various intellectual property licensing requirements, and then pull them together in ways that will be certifiable, will be high confidence, will be assurable, and legal as well. From the architecture point of view, again, there's these 3 different approaches. There's the engineering of societal scale software systems, which really means bringing together focus from the social sciences, psychology, sociology, economics, with people building software to try to do this in a way that's going to be more ethical, going to be more responsible. If I had to pick one topic that's probably the most important thing that we think about, it's probably that one, because you can see the consequences of what happens if you get it wrong, and we see those every day. As I mentioned before, engineering of AI-enabled software systems, trying to get these things to be as predictable and high confidence as traditional systems, which have a very different way of being developed. I work on a lot of mission critical and safety critical systems with the Software Engineering Institute, where we're basically precluded from using modern technologies, things like multi-core, things like shared caches, things like direct memory access, things like multi-threading, the kind of stuff that we would probably think of was really not all that modern in some ways. We're precluded from using those kinds of technologies because people haven't figured out how to assure them. And they aren't confident that they'll always behave the way that they're expected under any circumstance. Well, you can imagine how panicky people get when they start realizing that we're going to be using these deep learning algorithms and transfer knowledge algorithms in the way we build our systems, and all the uncertainty and potential non-determinism that creeps in. That makes people very, very nervous for obviously good reasons. And I mentioned before, new computational substrates like quantum computing, where the focus isn't really so much on the mechanisms of the hardware or the quantum physics, but more in terms of how do we program these things. And then once we start to program them, what are the software architectures we're going to need to make them scale, to make them be reliable, to make them be secure, to make them be predictable? Interesting, fascinating questions. So let's spend a little time now kind of doing a deeper dive into some of these areas. I won't go through all of them, but I want to focus on some of the ones I think are key for the future. So the first one is, how are we going to augment software development through, quote, AI-inspired or AI-augmented techniques? And basically, the point here is to figure out what parts of the software lifecycle lend themselves to these kinds of things. For example, do we think that we can let computers do the architecture part or the design part? Can computers and intelligent agents and so on help with other things, perhaps like quality assurance? Some parts are people are going to be more comfortable ceding to machines than other parts. And so we have to be very thoughtful about how we're going to do this. And part of the goal here, of course, is to do this in a way that will leverage all the advances in hardware technology like Moore's law, more transistors on a chip, more cores and so on, as well as more intelligent ways of taking advantage of those resources. Another key goal here is to figure out how to orchestrate the collaboration between computers and people. Who's driving the show? One thing we've often learned historically from studies of automation is when people start being de-emphasized, it often leads to very problematic safety problems because humans don't pay attention anymore. Good example would be train operators on trains that largely drive themselves, or pilots who are largely having the airplane fly in autopilot mode. People tend to zone out. So what's the appropriate mixture of what people do versus what computers do? And where do we draw the line in the software development lifecycle? You can imagine computers generating an awful lot of code that humans can't understand. That happens already with code generators and compilers nowadays and model-driven tools. But this is going to get even more pervasive. And so how are we going to keep a handle on that? And how can we express human intent in ways that are not so ambiguous as to make the code that comes out of the intent to code generator so fraught with ambiguity and so fraught with uncertainty that it's not actually useful? And this is where I think we really have to think carefully about what does it mean to specify something, how do we test something, what kind of confidence do we have in what's being produced with these kinds of approaches. So part of this process of doing this is going to really require rethinking the entire software lifecycle. If you take a look on the web, you can find all kinds of things about software lifecycle models, agile techniques, various ways of getting humans to work together effectively. How will that change when computers are assisting in more and more of that process? Finding out how to get data. One of the great things, of course, about deep learning and machine learning is if you can collect appropriate amounts of data, you can actually do a lot of analysis on it that will give you insights that very few people could ever have because they don't have a way to join across different data sets the way a computer can do. So thinking those issues through is going to be crucially important here. We're already seeing some interesting research on people doing things like mining GitHub repositories and trying to make estimates and predictions of where fault-prone software components will be based on things like frequency of check-ins or the types of comments that people put in when they commit their code and so on and so forth, which is a good example of AI-augmented software development. And then also, I think crucially important here, this is something that humans are very poor at, keeping track of details. People just don't like to track details. They like to do creative things. So as a consequence, are there things that we can have computers do to keep track of the details? And you see this more and more if you spend time programming with modern things like annotation-based dependency injection frameworks like Spring or Dagger, where an awful lot of what happens there is done behind the scenes, and they're repositories that are keeping track of dependencies in all kinds of ways. Humans are notoriously bad at that. Computers are good at that, but you also have lots of issues, as we'll talk about shortly when we talk about assurance and composition, of knowing what your system actually does when you start layering many pieces on top of it, not all of which were created by humans. So there's really literally nobody to ask, how does this work? So obviously having AI systems that can explain their reasoning are crucially important here as well. So let's talk about continuously evolving systems next. So pretty clear that in most environments, if a software system is successful, it's going to evolve. In fact, pretty much a hallmark of a successful system is one where there new demands, new requirements, new calls for porting to new environments from one platform to another, from a web-based system to a mobile system to different mobile systems and so on. And if you don't have evolution, it probably means that very few people are using your software. The problem is when you start thinking about evolution, especially in the context of these safety and mission-critical cyber-physical systems, where the right answer delivered too late becomes the wrong answer, we've got ourselves a real challenge because these systems are often very, very time-consuming and expensive to certify, and therefore people are loath to have to go through that certification process over and over again as the systems evolve. But systems have to evolve, if for no other reason that they have to continually have security patches applied to them at many different layers of the stack. And thinking about this topic, of course, requires a holistic view on both functional aspects, the requirements that you would have in your requirement spec, as well as the quality attributes, or the so-called non-functional properties, the ILTs, so dependability, reusability, scalability, and so on. So if we want to make progress in assuring these continuously evolving mission-critical systems, we really need to improve in two ways: have better theories of evidence and better theories of evolution. So theories of evidence really focus on how you take different types of evidence, where evidence would be things like the results from regression tests, or the results from some kind of static analysis or dynamic analysis, or the results from some kind of formal analysis, or the results from some kind of code inspection or code review, and so on. And then creating either automatically or semi-automatically formal or semi-formal arguments or assurance cases that give us better confidence that what we think the system does is indeed what it does, and try to weave together those different sources of evidence. Very, very hard thing to do today. You're lucky if you can get evidence from any one of those different sources and be confident in it, much less trying to combine them over time. And then the other dimension here that's tricky is how do things evolve and what happens as the system evolves. And of course, systems typically don't evolve in one fell swoop. You might have a hardware upgrade. You might have to move to a new version of an operating system. You might have new requirements that are going to be added either at the application level or the middleware level or the device driver level. And how do those changes have an impact on potential failure modes or vulnerabilities in the system? Very, very hard to do that analysis today. People build model-driven approaches and simulations where they can try to get a sense through the use of, say, digital twins. But the mapping between those simulations and the digital twins and the real system is often tenuous at best. So we need to think a lot more carefully about how we're going to map those things together. Obviously, there's a lot of room here for automation, being able to automatically generate some of these various sources of evidence, being able to keep track of those things, analyze them, cross-reference them, and so on. And then going back to the earlier topic about AI augmented systems, trying to combine expressions of human intent with the actual collected data in order to get a better insight as to what the system is actually doing and whether it's deviating from the expected behavior or whether it's conforming to it. And if it deviates, what to do about that. So huge issues in assurance, especially as things change over time. And obviously, again, this is an area where it's possible to leverage intelligent systems, especially data mining and deep learning and machine learning on collected data to get a better sense of the patterns that are happening that might be missed by human analysis. The next topic is one of my favorite ones. This is software construction through compositional correctness. This is something that I did when I was at DARPA many years ago. I ran a program that focused on things like multifaceted integration, what we would know as aspect-oriented programming. And basically the idea here is how can we raise the bar in terms of techniques and methods and tools and platforms for building and assembling systems out of components that get woven together in various ways. And the idea, of course, is we'd like to be able to build systems, integrated systems, whose properties, whose quality attributes are more robust than the components in isolation. Now, we do have some examples of this over the history of computing and networking. One of my favorite examples is TCP/IP. So the way the internet's built, as you all know, is that the hops between the nodes are prone to failure. They don't try to assure reliability at the IP layer. But the end-to-end behavior is reliable because they have built various types of retransmission techniques and other various networking protocol mechanisms like congestion control and flow control and sliding windows and so on, in order to be able to give end-to-end reliability over an inherently unstable infrastructure. And taking that as a metaphor, thinking about how we can do that at higher layers in the stack through component composition is crucial here. So sort of the holy grail of this approach is, and it's not unlike what we talked about before with continually evolving systems, is it possible to evolve system component implementations and or interfaces and or integrations, both at the functional level and the quality attribute level, so that the time required to recertify the composition of components will grow linearly or closer to linearly in the number of components as opposed to quadratically or exponentially, which is kind of the way it works now. So right now, people don't like to recertify things because it's hard to bound the scope of changes, because the mechanisms we use for defining components often leak information, and it makes it hard to compartmentalize and isolate the components so that changes will not percolate through their boundaries. So what are we going to need here? Well, we're going to need a theory of composability that supports a broader range of cross-cutting concerns and quality attributes. People who work in these techniques typically focus on a handful of attributes, largely in isolation. One of the things that DARPA has tried to do over time is to think again more holistically, but that still remains a difficult challenge, especially if you start looking at programming languages that don't lend themselves to various kinds of analysis effectively. So I'm thinking C and C++ versus, say, Java or other languages that are easier to analyze. Trying to come up with ways to document patterns, and then patterns of composition, and then, of course, reify those in the form of tooling that can specify and enforce composition rules. Come up with smart composition tools that can use AI or other techniques to be able to see what can be composed together, perhaps generating adapters and other ways of being able to connect things together, and then assuring these things at scale. And then also trying to get to the point where we can integrate all these capabilities in a common tool chain. Right now, each research community looks at a piece of the elephant, and it's often very hard to connect anything in an integrated way. I should also mention that there's a number of innovations in terms of how we program systems over the years that are helping with composition, but there's still many unresolved challenges. Probably the best examples are ModelDriven Engineering, which is a way of raising the programming language level to be more domain specific, and then what I call loosely annotation-based dependency injection frameworks, where rather than having a domain-specific language, you have your favorite language du jour, which could be Python or Java or, God help us, JavaScript, and you put annotations that are read by an annotation compiler that then generates large amounts of the code for you and then injects the various pieces together. These systems allow us to be able to put together kind of enterprise scale, web-based platform systems very rapidly. But the problem is they're devilishly hard to certify and validate without running the system, because there's so many layers of abstraction and so many different levels of indirection that it's hard to understand what the systems do to be able to analyze them and give feedback at a semantic level that's meaningful. So there's a lot of research that needs to be done to catch the assurance techniques up with the newer ways that we're building these kinds of systems. Okay, one more topic area and then we'll wrap up and take questions. So the fourth and final thing I'm going to talk about here are the emerging socio-technical systems that are at societal scale. So think of Facebook, think of Twitter, think of TikTok, think of all these things that we probably fritter away too much of our time being unproductive, trying to keep track of what's happening around the world. The problem is these systems have kind of taken on a life of their own, and they lead to very strange and often pathological dysfunctionalities. A good example would be GameStop, where people started to change the prices of stock in ways that were sort of crowdsourced. And whether you think that was a good or bad idea, it's just an example of how social media can be responsible for all kinds of interesting side effects that we might not expect. You can also think about protests and riots and civil unrest, where social media is used to either organize or disorganize things, and sources of disinformation and fake news and so on. So what's our role in all this? Well, from a software point of view, there's ways of building systems at societal scale that will behave correctly with respect to their functional and non-functional requirements. But there's also a series of ethical issues of privacy, bias, trust, trying to make sure that people know who's behind the information that's being put forward as truth, and not trying to let people manipulate things. And there's many, many examples, I don't have to spell them out for you, where people have leveraged social media platforms to give very biased information that has led to all kinds of crazy consequences. This is a real problem right now in healthcare. There's a lot of push by companies to get access to medical records of individuals and then do analysis of them to look for trends and patterns. Google Project Nightingale, if you want to find one example that's been in the news recently. These have raised serious ethical concerns and privacy concerns. So what we're going to need here, as always, is not just more programming languages, not more middleware or operating systems. Goodness knows we need more of those, of course. But we need a focus that's more holistic, thinking about economics, game theory, sociology, psychology, to try to figure out ways of harnessing the collective brain power of our academic community and other decision makers in industry and government to do a more effective job of building these systems. It would also be useful if we could experiment in these systems without having to unleash them in the wild, which is really what's happening now. So this requires thinking about software development that includes more dimensions of people, not just the tools, not just the languages. Thinking about a theory of sociotechnical epistemology, which is just a fancy way of saying, what's a justified true belief in this world of misinformation and this world of, quote, fact-checking, where it's never clear whether the people checking the facts are on the up and up? And also thinking about how do we balance different quality attribute trade-offs, one of which is conformance to regulatory policies. This is a huge issue right now that is in the process of being litigated in many courts around the U.S. in terms of privacy, in terms of large companies, the big tech companies taking information and using it in ways that aren't necessarily reflected in their terms and conditions. At least that's what the plaintiffs are arguing in this case. And of course, how can we try to detect and protect against misuse of these platforms? So to wrap things up, I have about a couple minutes left here. These are a summary of what will be in the study when it's released here shortly. First one, again, this is kind of restating the obvious. Software engineering and software is having a profound impact on many things. It's not just about compilers and analysis tools and middleware platforms and programming languages. It's about everything that we do as a culture, as a society, as an international planet, and so on. A lot of the things that are happening are taking place in the context of new and emerging system types, so automation, reassuring systems that have to evolve continuously. How do you compose systems out of building block pieces that you didn't write from scratch and may not be intended for composition, and so on and so forth. And if we want to be able to solve this problem, we're not going to be able to solve it in a completely homogeneous way. I think hopefully we've all realized there will not be one true programming language that dominates everything. There will not be one true operating system that dominates everything. There will not be one true smartphone platform or cloud platform that dominates everything, although people try. So we have to figure out about ways to work in a world of diverse elements, just like we do in everyday life, right? So diversity is part of everyday life in the human world and in the technology world. And we have to think about more than just the technical parts. We have to think about bias and privacy, transparency, freedom from bias, and so on and so forth. And this is going to require many different parties working together. Some parts of the world do a very good job of aligning government and industry and academia. I'll just pick on the Europeans because I think they do a good job of this. So when I was at DARPA, we used to go to meetings in Europe a lot and talk to our colleagues there. We were always very impressed with how well thought out those different pieces work together. Other places, sort of the US sometimes, we're not quite as well aligned. And there are good reasons for that. There are pros and cons, but we need to think more systematically about how we're going to bring all the different parties together to do something that will help us and not just cause more confusion down the road. Another thing that's pretty obvious, it's not just about sort of inward-looking omphaloskepsis, which is a fancy way of saying gazing at your navel. Basically, we need to think about how the work that we do in the research world intersects with other domains. This is crucially important. You see this from all the funding agencies. You see this in terms of what customers want. Customers and sponsors increasingly don't just want point solutions in isolation. They want integrated systems. And it's incumbent upon us as researchers to help make that easier. Not our responsibility entirely, but it will help if we can take a step in the right direction. Something else that's pretty obvious, software engineering is now international. It has been for a long time, but if you take a look at the innovation that's occurring around the world, if you take a look at who's publishing papers in top conferences and top journals, you see that it's a very, very international landscape. And there's ways, of course, of helping to facilitate more of that. Some of that has to do with the use of open source technologies, things like GitHub and ways of sharing information. Also just tools to allow people to work together harmoniously and be able to keep track of complicated issues in many different time zones. And then the final thing I'll mention before I wrap up and we do some Q&A, we really need to rethink how we're training our next generation workers. In fact, we also have to think about how we're retraining our current generation workers, because the technologies that are coming out here are complicated enough and ever-changing enough that you can't simply live on the patterns and languages and practices and platforms that you learned as an undergrad or as a graduate student 5, 10, 20 years ago. It's just not possible. So what can we be doing to make things better from an education perspective? Obviously, things like massively open online courses, MOOCs help. Nalini mentioned before, I have thousands of videos on my YouTube channel. If you look me up, you'll find thousands of videos there. But it's more than just putting the information out. We need to find a way to curate it. We need to find a way to help make it possible for people to get the on-demand knowledge they need when they need it in order to be more effective. And not just giving everybody little boot camp style insights that'll last you for a couple of months till that goes out of vogue. We need to think about ways of helping people understand the more foundational aspects. So lots of interesting challenges, and I hope that we'll all be able to work together to try to address them.